If you haven't yet seen my video on the index of hydrogen deficiency for hydrocarbons, take a moment to watch that now. Determining unsaturation from a chemical formula is simple enough when we have a hydrocarbon, but what happens when other elements are present? We know from our bonding lesson that the most likely elements in organic molecules are concentrated in that upper right of the periodic table. Carbon likes to make 4 bonds when neutral, nitrogen 3, oxygen 2, and the halogens 1. For this part of the lesson, let's abbreviate the halogens as X, a very common abbreviation. Okay, if any of the elements I've shown here are present, we're going to need to correct the saturated formula that we originally calculate. Now for nitrogen, we're going to add 1 hydrogen atom to the formula. Moving over 1, if we have an oxygen atom, do nothing to the original saturated formula. We won't add or subtract anything at all. Now if there are any halogens present in the formula, for each halogen, subtract 1 hydrogen atom. Now this correction has to do with the fact that nitrogen makes 3 bonds, oxygen 2, and the halogens 1 when they are neutral. Let's see why by looking at a few examples. Let's keep it simple with examples containing 2 carbon atoms. Ethane, our saturated hydrocarbon example, is C2H6, and it looks like this. Okay, so say we add a nitrogen atom here. We're going to have to add 1 hydrogen to our saturated formula, giving us H7. Okay, let's look at some possible structures for this compound to figure out why we had to add that H atom. If we imagine adding the nitrogen in the middle of ethane, we'll get this structure. Here's our skeleton, and nitrogen likes to have 3 bonds when neutral, so there's 1 H atom coming off of it. If we count up our hydrogen atoms, we have 3, 6, 7. There's one more possibility for our structure if we put the nitrogen at the end. Here's our skeleton. I've filled in the hydrogen atoms on carbon. And then, of course, our nitrogen likes to have 3 bonds. It needs to have 2 hydrogens on it. So we have 3, 4, 5, 6, 7 hydrogen atoms in this structure as well. All right, when we add an oxygen atom in, we don't have to change our formula. So let's look at C2H6O. For our first structure, let's imagine popping the oxygen in between the 2 carbons. Since oxygen likes to make 2 bonds when neutral, when we pop it in there, it has a bond to each carbon atom and therefore doesn't change the formula. We don't need to add or subtract any hydrogens. Again, with this formula, there's one more possibility for the structure, where we put the heteroatom, the oxygen atom, on the end. Our terminal carbon atom has 3 hydrogens to give it 4 bonds. This carbon needs 2, and we need to add 1 hydrogen atom to oxygen, since it likes to have 2 bonds when neutral. So this structure, which is dimethyl ether, or this structure, which is ethanol, are both possibilities for C2H6O. Okay, imagine we add a halogen now. Let's add bromine. When we do this, we'll need to subtract 1 H atom from our formula. So our formula is C2H5Br. The halogens like to make 1 bond when they are neutral. So the only place we can put the Br is on the end of the compound. We can't sandwich it in between 2 carbons or anything like that. So we'll just have one structure. We have 1 bond to this carbon and 2 bonds to this, so let's fill in so that we have 4 bonds. So basically in this structure, since bromine makes 1 bond, it's replacing a hydrogen atom. So we subtract 1 hydrogen atom from our saturated formula when we add bromine. Let's do a couple IHD problems to be sure we have this down. For example 1, let's do C2H4O. Remember our equation to figure out saturated compounds is 2N plus 2, filling in for 2 carbons, and then to correct for oxygen, we do nothing. So this is going to be the number that we use. Now let's do our Ihd calculation. So we take our 6 expected hydrogen atoms for the saturated formula, subtract it by the hydrogens in our actual formula and divide by 2, and this gives us a degree of unsaturation of 1. So we can have 1 double bond or 1 ring. There are a few structural possibilities for this formula. Let's start by looking at double bonds. First, let's imagine a double bond between the 2 carbons. We need to add 2 groups onto this carbon. This carbon already has 3 bonds, so we'll add 1 on. And oxygen likes to make 2 bonds when neutral, so we just need to add 1 bond onto the oxygen. Filling in our hydrogen atoms, we can see we have 4. Okay, oxygen makes 2 bonds when neutral, so it's possible the double bond is to the oxygen atom. That gives us this skeleton. We don't need to add anything onto oxygen because it already has its 2 bonds. This terminal carbon needs 3 groups, and this central carbon has 3 bonds and only needs 1. Again, let's add in our hydrogen atoms. So for our double bond examples, we have 2 possibilities. This compound, which is called an enol, and this compound, which is called an aldehyde. Now, it's also possible that we have a ring. We can pop an oxygen atom into the ring because it bonds in 2 directions. We can see oxygen is satisfied with its 2 bonds, but we need to add 2 bonds onto each carbon. This epoxide also satisfies our structural formula. Now let's do an example where we need to correct our saturated formula. Okay, we have 3 carbons. Let's plug that into our equation. Here's our saturated equation. This will give us 8 hydrogen atoms. But now we need to correct for bromine. So we need to subtract 1 hydrogen atom from our calculation that we just did. This is because bromine is going to replace a hydrogen atom. So with our correction for our saturated formula, we're expecting 7 H atoms. Now let's do our Ihd calculation using this corrected number. So we have 7 minus 5, which gives us 2. Divide that by 2, and we have an Ihd of 1. We have 3 carbon atoms. Let's start by drawing a structure that has a ring this time. Each carbon is bonded 2 ways and therefore needs 2 more substituents. We can put the bromine on any one of the carbon atoms and then fill in the rest of our hydrogens. We can also have a double bond between carbon atoms. Let's fill in 4 bonds for each carbon atom. Now we have a lot of possibilities for this compound. The bromine can be placed on any of these carbon atoms. And we get a distinct compound if we place it on this terminus, the central carbon, or this terminus. Let's put it in the center as one of our examples. So with the double bond, we have our 5 expected hydrogen atoms. And to complete our story, here are a couple other structural possibilities by putting the bromine in different spots. In this lesson, we looked at how to calculate the number of hydrogen atoms on a saturated hydrocarbon using the number of carbon atoms in the structure. We looked at how to correct our formula for some of the common elements we'll see in organic compounds. We looked at the structural origin of this and did a few practice problems. KP here. If you learned something, give me a thumbs up on the way out, and for more chemistry, subscribe to my channel.